Sidhanth here, and today we will talk about certified counting in random constraint satisfaction problems. And this is based on joint work with Tim Shea and Jeff Shue, who are both graduate students at Carnegie Mellon. Today the main object of study is going to be a random 3-sat formula. So, in a random 3-sat formula, you have n variables and m clauses, and each clause is drawn independently by first choosing 3 variables, each one uniformly at random from 1 to n, and then placing a random negation pattern on these variables. And the main phenomena related to random 3-sat that we'll be interested in is that of phase transitions. Now, the most fundamental phase transition is what is known as the satisfiability threshold. In particular, when the number of clauses m is smaller than a certain threshold 4.27 times n, then the 3-sat formula is going to be satisfiable with high probability. And when this number is larger than 4.27 times n, then it's actually unsatisfiable with high probability. Now, working towards the kinds of thresholds that we'd be interested in. So we know that 4.27 times n marks the onset of unsatisfiability. But let's say you're given a formula which we know is in the regime where it's going to be unsatisfiable with high probability. We are interested in the algorithmic task of once the randomness is quenched and you're face to face with the random formula, you want to give a proof that this formula is unsatisfiable with high probability in polynomial time. Particularly, you want to certify unsatisfiability. And we know algorithms to certify unsatisfiability, also known as to refute a random 3-sat formula, once the number of clauses exceeds n to the 1.5. And actually, when the number of clauses is smaller than n to the 1.5, we have some sort of hardness evidence. And this hardness evidence comes in the form of lower bounds against restricted class of algorithms, such as sum square semi-definite programs. The property of 3-sat that we're going to be interested in is the number of satisfying assignments that the formula has, which I guess in some of the literature is called the partition function at 0 temperature. Now, the number of satisfying assignments exhibits the curve where when you have no constraints, every assignment you can think of is going to be satisfying. So it's going to be 2 to the n satisfying assignments. And as you add more and more constraints, the number of satisfying assignments increases. And once you cross 4.27n, it eventually becomes 0 and stays 0 forever. So now the question is, can we certify number down on the number of solutions in polynomial time? So refutation is actually a special case of this question, where once you exceed n to the 1.5, we actually have algorithms that can certify that there's literally 0 solutions. But let's say you are in the regime between the satisfiability threshold and the refutation threshold, then what can you say? In particular, in that regime, we know that with high probability, the formula is going to have 0 solutions, but from the lens of a polynomial time algorithm, we don't necessarily know that. So now let's make the definition of a certification algorithm. So given a formula phi, we want to say that an algorithm A certifies that this formula has at most k satisfying assignments with high probability over the randomness of a distribution D that the formula is drawn from. If you have the following 2 guarantees for the algorithm, for any formula phi which you could have gotten, you want to be the case that this algorithm, which outputs a number, the number outputted by the algorithm always exceeds the number of satisfying assignments. And second, you want the number output by algorithm to be at most k with high probability over the randomness of this formula phi. So, such an algorithm you can think of as giving you a proof that a random formula has at most k solutions. And this crucially relies on the fact that this algorithm is always correct. So, in particular, always being correct enables you to use the trace of the algorithm itself as a proof that a formula has at most k solutions. Okay, so now let's consider two really trivial algorithms and see why they fit or whether they don't fit the definitions. So, one of them is to always output the number 0. So, always outputting 0 actually violates correctness because if I feed a satisfying a formula which has a satisfying assignment, then it has at least one solution, and 0 is an incorrect upper bound. Uh, and on the other hand, if you always output 2 to the n, yes, you are giving a correct upper bound, but you're not saying anything useful about the satisfying assignment. You're not saying anything about the structure. So in our work, I want to reiterate that we focus on the unsatisfiable regime, and this would be the region in between n, the satisfiability threshold, and n to the 1.5. And we'd like to determine the curve, which is what is the best upper bound we can certify on the number of satisfying assignments. And a couple of candidate parameters that you might guess is maybe when the number of clauses is smaller than n to the 1.5, then you can't certify any non-trivial upper bound. And once you exceed n to the 1.5, you can use your refutation algorithms. So this would mean there's a sharp drop to 0. Another possible universe might be one where the bound that you can certify when the clause density is roughly constant, or in particular when you have a roughly the same number of clauses and variables, you certify an exponential bound, and as you increase the number of clauses, you smoothly interpolate between exponential and 0 in some particular way. But actually, a theorem shows that neither of these two intuitive universes is what actually happens. So, in particular, our algorithm does have some sort of smooth interpolation between the SAT threshold n and the refutation threshold n to the 1.5. And the interpolation happens between 2 to the n and 2 to the n to the 3 quarters. But beyond n to the 1.5, there is a sharp drop in what you can certify. In particular, you can refute, and you get a sharp drop from exponential and n to the 3 quarters to 0. Now, this may seem like a suboptimality of the algorithm, but actually, we believe that this is tight, and we have some hardness evidence for this. In particular, if you could beat this curve, then you would also be able to actually refute 3 SAT under the n to the 1.5 threshold. Okay, so far we have sort of illustrated what efficient algorithms see in terms of the number of satisfying assignments. But can efficient algorithms also certify anything about how these solutions are distributed in space on the Hamming cube? In particular, do these potentially 2 to the n to the 3 quarters solutions just live in one large cluster? Or do they form a bunch of small clusters which are far apart from each other or are all the solutions pairwise far apart from each other? And actually, let's get some slight inspiration from what happens in the in the regime where we actually have satisfying assignments. It turns out that there's several phase transitions for what the solution geometry looks like. In particular, when the threshold is low enough, you have one giant component of solutions, and then the solutions form exponentially many clusters which are far away from each other, but each cluster has exponential size, and so on. And we show the following in terms of what an efficient algorithm can see in terms of the number of clusters. So, given a random 3-SAT formula, we actually once again give a smooth interpolation between the number of clusters that you can satisfy and the number of clauses. And in particular, this interpolation happens between 2 to the n closest SAT threshold to 2 to the square root n at the algorithmic threshold. And an algorithm can certify that there's at most exponential of n to the half plus delta over 2 diameter uh, n to the 3/4 plus delta over 2 clusters. And note that this actually implies theorem 1 because we know that any given cluster can have at most exponential in 3/4 plus delta over 2 many clusters. And the number of clusters is strictly lower order. So now let's go over some of the ingredients that we use to prove theorem 2. And the first ingredient is what we call the 3 XOR principle. So far we were talking about 3-SAT, but the 3 XOR principle sort of tells us something nice about satisfying assignments in 3-SAT formulas which are fairly dense. In particular, if you have a random 3-SAT formula on delta times n clauses, we can actually certify the following about any potentially satisfying assignment to this formula phi. That is, if there's a satisfying assignment to phi, it actually also must satisfy phi if you look at phi as a 3 XOR formula rather than just a 3-SAT formula. And in fact, this reduction is more general. If you have a k-SAT formula on up to square root and below the refutation threshold, then you can actually certify that any satisfying assignment to this k-SAT formula must satisfy most clauses as k-XOR. Okay, so the fact that any satisfying assignment must satisfy most clauses 3 XOR sort of lets us study 3 XOR instead. In particular, given a random 3 XOR formula, we'd like to certify bounds on the number of 1 minus 1 over square root delta satisfying assignments. So here's theorems 1 and 2 for 3-SAT, just rephrased for 3 XOR. So now, the next step is going to be about certifying some lower bound on the Hamming distance between solutions. So here's what we would actually want to certify. Let's say you're given a random 3 XOR formula phi, and you also have two satisfying assignments, x1 and x2, which satisfy almost all the clauses of phi. In particular, they 1 minus 1 over square root delta satisfy phi. then we want to say that x1 and x2 are either very close in Hamming distance, which is they agree on uh, almost all except 1 over square root delta fraction of the coordinates, or they're pretty far in Hamming distance. Namely, the Hamming distance is close to a half. It's like half plus minus 1 over square root delta. So if you think of delta as being like something super constant, then it's basically saying that like x1 and x2 are either very close or roughly half apart. So in particular, this already tells us that from the lens of an efficient algorithm, all the solutions kind of live in uh, small clusters. These clusters have diameter at most 1 over square root delta, and also these clusters are pretty far apart. Now, these clusters being pretty far apart is going to let us certify an upper bound on the number of clusters. So let's see how to do that. Let's say we take one vector from each cluster, then uh, all pairs of vectors in this collection that we just created must be pretty far apart. They must be pretty close to half far apart. In particular, their pairwise distances have to be at least half minus 1 over square root delta. And there's a classic result from coding theory, which which tells us that the number of code words, in particular the collection of vectors that we choose, has to be at most exponential in n over delta. And and hence, uh, we know that there's at most 2 to the n over delta clusters, and each cluster has diameter n over square root delta. Now, diameter n over square root delta ball contains at most 2 to the n over square root delta binary vectors. Uh, and so the number of satisfying assignments is bounded by 2 to the n over square root delta. So that's it for the technical parts. Now I want to finish this talk with 2 open questions. So while we did have hardness evidence for against improving the 2 to the n to the 3 quarters edge for the certified counting question, the 2 to the square root n does not seem inherent for the clustering question. So one question is whether one can prove some sort of hardness evidence to show that the algorithm we gave to certify a bound on the number of clusters is nearly tight, or one could try to give an improved algorithm. We actually think that the truth, in some sense, is that there is an improved algorithm, and in fact, we believe that there should be an algorithm that can certify that there's only a constant number of clusters of solutions. So that would be an interesting open question. And the second question that I'd like to ask here is a worst case question. So we know that distinguishing a 3-sat formula that is 7/8 plus epsilon satisfiable from one that is satisfiable is actually NP hard. But let's say I actually promised to you that the 3-sat formula I give you is either 7/8 plus epsilon satisfiable, uh, or it's actually not just satisfiable, it has many solutions as well. It has at least t solutions. So, for how large of a t can you algorithmically distinguish between the two cases? And thank you, and feel free to email any of us if you have questions.